Hello everyone. My topic for presentation is lensless microscopy using Fresnel zone plate photomask modulation. I am student of MS Physics, COMSATS UC Islamabad, and my supervisor Dr. Ahmad. The components provided for this research by the potential and electrical system and table of contents, which I will present in this presentation is, first of all, I will introduce my topic, and then I will say something about the lensless microscopic setup, and then I will discuss the Fresnel zone plate, and after that I will discuss the imaging model, and at the end I will discuss results and conclusion of my presentation. So in traditional microscopy, the point-to-point imaging model has been followed, and which were the limitation there are collection of the rays and converging of that rays is the limitation of the traditional optical microscope, which required the expensive and bulky lenses, and the resolution is dependent upon the numerical aperture, and the resolution and field of view in the traditional microscope is inversely related or coupled to each other, and we cannot handle 3D imaging very easily in the traditional microscopy. That's why in lensless microscopy, the geometry is very much simple and the size is compact, and which is portable. We can use it anywhere, and the cost is very much effective. Low cost, at low cost we can buy it, and the field of view in the lensless microscopy is very much large, and the resolution we can achieve is high, which is independent of the field of view in the lensless microscopy, and the imaging, the 3D imaging we can achieve very easily. So why coded aperture replaces the pinhole? As the pinhole has simple architecture, infinite depth, and no aberration, but the only thing through which the coded aperture suffers is the light throughput, means we cannot take the image of the whole object easily. We have to use large number of pinholes to take the image. That's why the coded aperture mask, which is the unique shadow of the mask onto the sensor, which is encoded the intensity and the location of the light source. In my proposed work, we use the lensless imaging system, and the incoherent illumination is used over there, and we use the Fresnel zone plate to encode that illumination, and then we take a single shot and reconstruct that single shot and suppress its noise, and which is the lensless setup is very useful for the most sensitive tissues to capture its image, because we use a very very high wavelength light, means we use the green LED, which have low energy, and red, which has also very low energy here. We use the special light modulator here to modulate the light and apply a mask over there. We use the special light modulator modulate the light specially, and it modulates the phase of the incoming light, and which we can use the SLM we can use also for the holographic display. And in our case, the SLM is if modulate the phase from 0 to 1.2 pi, and we use it through MATLAB through its own software. This is the schematic diagram of our lensless setup. Here we use an illumination source, then we used a polarizer over there and to polarize the light, because in our case the mask, the SLM works only on the polarized light. And then we use an analyzer, and at a distance of 15 millimeter we put the object over there. The object we use the USAF 1951 resolution chart in the transmission mode. Then we put the sensor at 0.987 millimeter. Then the lensless microscopic experimental setup of the lensless microscope is, it is the illumination source. Here we put an illumination source, then the polarizer we put there, and then in SLM is used over there. We apply any mask, any type of mask over there at the SLM, and then we put an analyzer and an object over there, and the CMOS sensor is used there to record the images of the object. Now let me to discuss the little bit about the Fresnel zone plate. A Fresnel zone plate is only an optical instrument that work on the principle of diffracted light waves, and it is consist of opaque and transparent zones. When light rays come and it diffract at the edges of the opaque zones, so an interference pattern forms over there, and the constructive and the destructive interference is we can't see this destructive interference there, but at a specific point at which we have to focus the light, the interference pattern occur over there. The construction of the Fresnel zone plate depends upon this equation, where R1 is the Fresnel zone plate constant. This R1 is the Fresnel zone plate constant, because the whole Fresnel zone plate depends upon this R1. If we increase R1, then the zones will increase or decrease. If we decrease this, then all the zones will decrease or increase. R2 here is the distance from the center of the aperture to the outermost zone, and which is written is this, like this. The transmission function of the FZP is this one, where T of R is the transmission function, and R1 we use is radius of the innermost zone, and R2 is the rated distance from the center of the aperture. How the resolution of the FZP is dependent. We used in our experiment, we used different R1, different FZPs which has different R1, and the resolution, and the resolution there is depends upon this equation, where R2, if we have n number of zones in the FZP, then R2 is equal to this, and delta of R is approximately equal to this. Here delta of R is width of the outermost zone, and the resolution then depends upon the delta of R, the width of the outermost zone. Let me discuss the imaging model. Here the forward propagation, we calculate the mathematics for the forward propagation is this. Here this is the equation for the incoherent illumination, and this is the transmission function of the mask. When this propagate and the light propagate towards the mask plane, then the fields in the mask plane is the product of the illumination source and the transmission function, and then if 2 is the field over here, which is the convolution of the F1 field and the PSF1, point spread function 1, and F3 is the plane over the object where the F2 field and the object combine there, and it's take the information from there and propagates towards the sensor, where F4 field is the convolution of the point spread function 2 and F3. Here the intensity is recorded toward the sensor, and which is the mod square of the F4. Then we back propagated this light, and then we take the square root of the intensity, and F3 we take the conjugate of the PSF2 and convert it with the F4. Then F2 prime is the object multiplied with the F3 prime. Then we get the final image of the object, which is as shown here in this equation. Now let's discuss the results. Here in simulation results, we construct different zones, different Fresnel zone plates. There, first is 0.35 millimeter, and the second one is R1 0.55 millimeter, and the third one is 0.75 millimeter. Here we can construct the simulation. First, the amplitude. Here, amplitude images are shown over here, which shows that it's 0.35. If we take the innermost radius of the zone 0.35, then the image will be so clear. And after, if we take 0.55 millimeter, increase the distance of R1, then the image will be a little blurred. And if we take the 0.75 millimeter, then there the noise there increase very much. Here, these are the phase images. As light waves consist of amplitude and phase, so we can and I cannot detect the phase, only it detects the amplitude. So we reconstruct the image and construct its phase from the image. So the phase here, it shows that if we take the innermost radius of the FZB 0.35, then the images are here, the resolution there is better, and as we increase R1, the resolution is getting worst. So here quantitatively we compare the peak signal to noise ratio of different FZBs, which shows that as we increase the value of R1, then as we increase the value of R1, then the peak signal to noise ratio is decreasing, which shows that we have to take the value of R1 small, then the resolution there will be very better. Here, these are the experimental results of my experiment. It's the captured image we captured through the CMOS sensor. Then after reconstruction, the resolution is very much better, and the noise there is a little bit, but we remove a lot of noise from this image. And the fifth group of the USAF 1951 resolution chart is resolved to a better extent, and these results are at R1 0.35. Then we take the images through R1 0.55 millimeter, and then on 0.75, sorry, this is 75 millimeter. So the conclusion of my presentation is we have constructed a portable and cost-effective setup of the lensless image, and the PSNR value is decreasing, which clearly shows that PSNR value is decreasing by increasing the value of R1, and the Fresnel zone plate can be used in the lensless setup to achieve the high resolution. And in the future prospect, we will advance our system to take images of the movable object, and our system will be able to achieve the high resolution of sensitive tissues without harming. Thank you so much for your attention. If any question is there.